Okay, we're going to go on here to the second part of Chapter 8, and mostly what will be covered here will be some different points of interest regarding Pearson's R. So a first point to understand is that neither adding nor subtracting a constant from all scores will affect the value of R. So that suppose for whatever reason you added 1 inch to each high jump height that you had measured in a study. Doing so would not affect the correlation of high jump height with any other variable. Now similarly, you could take, for instance, high jump height, and you could multiply each person's high jump height or divide by a constant, and neither of those would affect R. So that, for instance, perhaps you measured height in feet, but you think expressing height in inches would be more effective. Well, you could measure all of your you could multiply all of your high jump heights measured in feet by 12. You'd be converting to inches, and then you could correlate high jump height measured in inches with a variety of other variables. And high jump measured that way would correlate precisely the same as would high jump measured in feet, that is, before you multiplied by the constant 12. Now, just to give you some sense of why you can add or subtract a constant, or why you can multiply and divide by a constant, and this doesn't affect R, recall that z-scores are used in the formula for R. So, I mean, it is indeed the case that neither adding nor subtracting or multiplying or dividing by a constant affects z-scores. So, for instance, multiplying all of our high jump heights by 12 wouldn't change z-scores. I mean, one could then go ahead and convert the high jump height measured in inches to z-scores. The high jump height z-scores converted from inches, those z-scores would be precisely the same for each case as the z-scores you would get if you had high jump heights measured in feet and used those measurements to compute the z-scores. In some, I mean, it's a nice feature that neither adding nor subtracting nor multiplying or dividing by a constant affects the value of R. As I mentioned in the last video, R is a workhorse measure. It's used again and again, and one of its great features is that its value may vary from -1 to 1. So those are clearly very easy numbers to remember. The closer that the absolute value of R is to 1, the stronger is the association between the two variables that are involved. So to demonstrate, let's look at each of these pairs of values of R and find the R within each pair that conveys the stronger relationship between two variables. 0.3 versus 0.7. An R of 0.7 conveys stronger association than does an R of 0.3. How about -0.6 versus -0.2? Well, it's the absolute value of R that's conveying the size of the association. So therefore, -0.6 conveys stronger association than does -0.2. The absolute value of -0.6 is 0.6, and that is closer to 1 than is the absolute value of -0.2. For this third pair, 0.5 conveys stronger correlation, which is to say stronger relationship between two numeric variables than does 0.2. And in this final example, the absolute value of -0.5 is 0.5, so therefore -0.5 conveys stronger relationship than does 0.2. Let's talk about some particular values of R. Correlations of 1 and of -1 are termed perfect correlations. In a perfect correlation, you have in essence perfect predictability, which is to say, with perfect correlation, the markers on a scatter plot will line up exactly along a straight line in the scatter plot. And the next slide will convey that. Now we're going to discuss an exception later on, but for the most part, a correlation of 0, that is where r equals 0.00, this is conveying the absence of association. In this situation, we've got no predictability at all. So knowing one's score on x helps not at all in predicting score on y. And we'll take a look at the scatter plot that we often see where correlation is 0, and we'll talk about an exception later on. So the upper left figure is conveying perfect positive correlation, r equals 1.00, and you can see that the markers on the scatter plot line up precisely in a straight line, and that straight line goes from lower left to upper right. And perfect negative correlation, so the slide is wrong here. I mean, this is perfect negative correlation, which is to say an r of -0.1 occurs when you have the dots lining up precisely on a straight line, and the slope of that straight line is from upper left to lower right. Now, when you have correlation of 0.00 or very close to that, almost always, if you were to have the computer produce the scatter plot depicting that correlation, that scatter plot will have a pattern that is, in essence, random. And I mean, I like to think of it like the buckshot that would come from a shotgun. That the pellets from the shotgun sort of scatter randomly around the target at which the gun is pointed. But you can see the absence of predictability as we go from left to right on variable x. Is there an appreciable change in the distribution of scores on y? And you can see clearly not. I mean, where x is low, I mean, y is spread out, and then here where x is in the middle, y is similarly spread out, and similarly the shape or the position of the dots in the scatter plot where x is high is very similar to that where x is medium or x is low. So we have this buckshot pattern, this absence of predictability. You know, now we have more dots in the middle of the scatter plot, but I mean, the distribution of those dots is very similar at low, medium, and high values of x. Here are some descriptors of size of association for R. 1 conveys strongest possible positive relation, -1 strongest possible negative relationship. So just you know, summarizing our way through these approximations, and these qualitative descriptors are basically approximations. I mean, helping you get a feel for size of association. So if you get a correlation of about 0.1 or about -0.1, I mean, and indeed those each convey the same size of association, basically those values are fairly close to 0. So they're fairly close to that non-predictability buckshot pattern that we just looked at. So the correlations of about this magnitude are deemed small, and where correlation gets to be closer to 0 than these values, the association starts to be so small or that it becomes almost trivial. So this is almost like a little cutoff. When the correlation gets below this, you really start to say, well, the size of association is very, very weak between the variables. And so here's sort of the opposite, where the highest correlation can get in terms of absolute value is 1. So here we're starting to get quite close to 1, and this is correlations of about 0.7 or minus 0.7 are clearly very large associations. I mean, you do sometimes see correlations this strong between variables, but certainly in social science research, these are at least somewhat uncommon. So the guiding idea is going to be that the larger is the absolute value of r, the more the dots on the scatter plot are going to line up narrowly in the form of a line. Now, with a little bit of practice, you know, you're going to be able to look at a value of r. I mean, in other words, the value of r is going to be, let's say, 0.10, which is what's conveyed in our upper left scatter plot here. And you're going to be able, in your mind's eye, picture the shape of the pattern of dots in the scatter plot. So you know that 0 is most often that buckshot pattern, and you know positive correlation slants from lower left to upper right. So this correlation of 0.1, it's very close to 0, so that conveys a wide spread to the dots, and then the correlation is positive, so that's conveying just a hint of positive slope. As x goes up, the pattern is for values of y, very gradually to march upwards. Oh, let's jump ahead here to this strong positive correlation as approximated by our descriptors. And here you're starting to see the dots are indeed beginning to line up in an oval-like pattern around a straight line that goes from lower left to upper right. Now, were you to read in a journal article that the correlation between x and y was 0.50, your mind's eye could perhaps picture a scatter plot that would look something similar to this one. And then finally, here is our strongest positive correlation in terms of the qualitative descriptors that we're using. And here we're really starting to see a very strong lineup of the dots along a straight line. And I just will mention that it is usually a good idea in doing research to go ahead and create a scatter plot. Here we are looking at negative correlations that correspond to the 4 levels of size of association. So here is our small, or we can say weak negative association, correlation of minus 0.10. Here's our medium or moderate negative association, correlation of minus 0.30. Here is our strong negative correlation of minus 0.50, and here is our very strong negative correlation, minus 0.70. So everything is the same here as was the case with positive association. The difference is that the slant of the dots is from upper left to lower right. And note that we see the same pattern, that as the correlation gets stronger, as it gets closer to minus 1, the dots scatter less and less around an imaginary line that would slice the negative slope conveyed by the correlation. So here are our most tightly clustered dots corresponding to correlation of minus 0.70. Here's a little exercise that we can kind of talk our way through. So our unifying idea, the larger the absolute value of r, the narrower the oval formed by the dots of the scatter plot. How strong of a relationship is conveyed by each of these values of r? And really here, I guess what we're doing is referencing those qualitative descriptors that were just presented. So if you see an r of 0.51, that's clearly positive relationship, and that's strong positive relationship. we were just talking about a correlation of minus 0.70. That's a strong negative correlation, which is to say it conveys strong negative relationship between two variables. And correlation of plus 0.30 is a medium-sized positive correlation. Now, minus 0.04, I mean, this is a negative correlation, technically and formally speaking, but do see how close this value is to 0.00. So this is not meeting our criterion even for small size of association. So this correlation here this relationship is presumably trivial in size, and we're going to make a talk a little bit later about some exceptions. Minus 0.63, again, this is a negative relationship that is quite strong in terms of our qualitative descriptors. So here's your trick question. What would you say if you were asked on the test how strong of a relationship between two variables is conveyed by an R of 2.83? So the key point here is that R may vary from minus 1 to plus 1. I mean, there is no such thing as an R of 2.83. I mean, this must be a typo or a miscalculation or something similar. So I guess your best answer on the test would be there is no such thing as a correlation of 2.83. And finally, here is a very strong positive correlation, a correlation of 0.83. This text uses the actual value of R as a guide to assessing strength of or size of association. Now, it is also common, perhaps more common, to square R and use the squared value of R to assess strength of association. So when you square R, that is, when you calculate R squared, you calculate what is called the coefficient of determination. And R squared conveys the proportion of variance that two variables share. So expressing correlation in terms of its squared value, this is an alternative way to express size of association or strength of association. Now, what's tricky about this is that, when you, in terms of absolute values, when you square R, I mean, except when R is 1 or minus 1, other than that, in those situations, when you square R, you get a smaller value. So, for instance, were you to have an R of 0.3 and express that R as the coefficient of determination R squared, you'd multiply 0.3 times 0.3, and the coefficient of determination would compute to 0.09. So that's conveying to you that the two variables share 9% of variance with one another. I don't like variance as a measure because I think it's more mathematical than intuitive. And by the same token, R squared is not my favorite measure. I mean, I like R because there's such a great correspondence between the shape of the dots on the in the scatter plot and the value of R. So when you look at R and you see R changing in value, your mind can picture the scatter plots either tightening to a narrow oval, or if it's a value of R close to 0, spreading out more like the buckshot pattern. So you have no such visual, intuitive equivalent with R squared. And that's why I don't like it. But suppose that a test question were to query which value conveys the stronger relationship between two numeric values, an R of 0.3 or an R squared of 0.09. And the answer would be, well, these two are conveying the same size of association, the same strength of association. They're just different ways for expressing strength of association. And let's do one more calculation of R squared. if r were to equal minus 0.5, what's the value of r squared? Minus 0.5 times minus 0.5 equals 0.25. So r squared equals 0.25. And again, these are different ways to express strength of association. And r of minus 0.5 conveys the same strength of association as does an r squared of 0.25. Suppose that in reading the literature you come across a value of r squared, and then you want to make some kind of rough approximation in your mind of what is the strength of association conveyed by this r squared. Well, what you'll need to do is to calculate a square root, and then check that square root off against the table of qualitative descriptors. So, I mean, if you saw, for instance, that r squared equaled minus 0.09, you could take the square root of 0.09, and that would equal 0.30. At least that's the positive square root. And minus 0.30 is the negative square root. We don't want to get tangled up in all of that. But the positive square root will work just fine for conveying strength of association. So, you know, you'd calculate that positive square root of 0.30, and then you could reference the chart of qualitative descriptors, and this is a correlation that is expressing a medium strength of relationship. I want to offer one caution to you as you interpret strength of relationship from R, and that is that very low variability in one or both variables almost always reduces the absolute value of R. So here's an example. You are teaching a child development class to a group of new parents, all of whom are highly motivated. I mean, perhaps your class was very, very hard to get into, and only a few people could get in, and everybody who's getting in really is motivated to learn about child development. So then ask yourself the question, do I in this class have much variability with respect to motivation? And the answer would be no, because in essence all of the students are very highly motivated. So there's very low motivation variability. I mean, people are highly motivated, but the amount of motivation varies hardly at all. Now then, you have an outcome measure to measure perhaps learning or knowledge in child development. And what you're wanting to do is you're wanting to look at, well, is there a relationship? And if so, how strong is the relationship between level of motivation and, say, score on the knowledge test? It's almost assuredly the case that the correlation that you compute between motivation and knowledge will be fairly close to zero. I mean, you will likely find a weak positive correlation. Now, the reason that the correlation would come out to be fairly close to zero is that in your situation, level of motivation almost isn't a variable at all. Because motivation variability is so small, motivation is almost a constant. Now, if you were teaching a class and there was within that class a large amount of variability with respect to motivation, in other words, there's some low motivated, medium motivated, and some highly motivated people, in that situation, my best guess is that you would find a strong positive correlation between motivation and knowledge. I mean, the people who are highly motivated would gain greater knowledge than with those who were not. But the gist of this is that when you have a situation where you have very restricted or compressed variability on one or both of your variables, that compressed variability pushes the value of R towards zero. And in essence, you get a result that it seems to suggest that the relationship is is quite weak, and indeed the relationship is very weak in your sample. But do recognize in this situation that if you had a different sample and the variability was quite good on both of your variables, the value of R that you get would almost assuredly, what I want to say is the absolute value of R that you'd compute would almost assuredly differ more from 0. I mean, you'd get a stronger relationship. The next video in Chapter 8 is going to move on to talk about regression. And before we do that, I just do want to make a quick point to say that R is measuring the degree of linear relationship, the degree to which, in essence, the dots of the scatter plot array themselves along a straight line. How close do they cluster along a straight line? But it's not always the case that the relationship between two numeric variables has a linear, which is to say a straight line form. So R's not a good measure of relationship when the pattern of that relationship is nonlinear, which is to say when it doesn't follow a straight line. And we'll be talking about that a little bit later. But the next video is going to pertain to regression.